on scalar triple product. For three vectors A vector, B vector and C vector, A vector dot B vector cross C vector is the scalar triple product. It is denoted as square bracket A vector, B vector, C vector. These are some points which we have to remember with respect to scalar triple product. The scalar triple product is a scalar quantity, which means there is no direction associated with this quantity. The third factor is that if A vector is equal to A1i plus A2j plus A3k, B vector is equal to B1i plus B2j plus B3k, and C vector is equal to C1i plus C2j plus C3k, then the scalar triple product A vector dot B vector cross C vector is denoted as determinant of A1, A2, A3, B1, B2, B3, C1, C2, C3. So we will also find that A vector dot B vector cross C vector will also be equal to B vector dot C vector cross A vector, which is also equal to C vector dot A vector cross B vector. So it goes as a cycle ABC, ABC, BCA and CAB. It goes as a cycle. Also, A vector, B vector, C vector is equal to minus of A vector, C vector, B vector, because you know that A vector, B vector, C vector is equal to A vector dot B vector cross C vector, which can be written as A vector dot minus of C vector cross B vector, because B vector cross C vector is minus of C vector cross B vector. This will become minus A vector dot C vector cross B vector, and therefore this is equal to minus of A vector, C vector, B vector. So this is a very important property. Similarly, the fifth property says that A vector, B vector is equal to 0. So whenever two vectors in this is same, it becomes 0. So how to prove this? See, very simple. This is according to the cycle. It can also be written as B vector, A vector, A vector, because we saw that ABC can be written as BCA, which can also be written as CAB. So ABC, BCA, CAB, it becomes a cycle. So in the same way, AAB can be written as BAA. So this is actually equal to B vector dot A vector cross A vector, and cross product of the same vector is always 0. So this is B vector dot 0 vector, which is 0. So whenever two vectors are same, the scalar triple product will become 0. Then the sixth property is that three vectors A vector, B vector, C vector are coplanar. Coplanar means they lie on the same plane. That is, they lie on the same plane. So three vectors are said to be coplanar if their scalar triple product is 0. If A vector dot B vector cross C vector is equal to 0, then the three vectors are said to be coplanar. And the last point, 4 points A, B, C, D are coplanar if AB vector, AC vector, AD vector are coplanar. That is, we have to prove that AB vector dot AC vector cross AD vector is equal to 0. If this is 0, then the three vectors are coplanar and the 4 points are also coplanar. So with this introduction to scalar triple product, we can try to solve some problems. So there are 7 important properties in scalar triple product, after which the problems are very easy. Let us now start doing problems in exercise 12.5. The first sum 10.5. First sum, find a vector, b vector, c vector if a vector is given to be I minus 2j plus 3k, b vector is given to be 2i minus 3j plus k, and c vector is equal to 3i plus j minus 2k. So given this problem, we are simply asked to find the value of a vector, b vector, c vector. So according to the definition, it is determinant of 1 minus 2, 3, 2 minus 3, 1 and 3, 1 minus 2. So that is going to be equal to, according to the determinant property, 1 into 6 minus 1 plus 2 into minus 4 minus 3 plus 3 into 2 plus 9. This comes out to be 5 minus 14 plus 33. That comes to be 38 minus 14, which is equal to 24. Very simple problem. Let us go to the second problem. Show that the vectors a vector is equal to I minus 2j plus 3k, comma b vector is equal to minus 2i plus 3j minus 4k, c vector is equal to I minus 3j plus 5k are coplanar. If they are coplanar, we have to show that the scalar triple product is 0. So let us calculate what is the scalar triple product, a vector, b vector, c vector. So that comes out to be equal to the determinant of 1 minus 2, 3, minus 2, 3 minus 4, 1 minus 3, 5. That is equal to 1 into 15 minus 12 plus 2 into minus 10 plus 4 plus 3 into 6 minus 3. That is equal to 3 minus 12 plus 9, which becomes to be 0. Therefore, a vector, b vector, c vector are coplanar. Because for the condition of coplanarity, the scalar triple product has to be equal to 0. Let us do the third sum. Find lambda if the vectors are coplanar. So it is given in the problem that the 3 vectors are coplanar. So we have to simply find the lambda. So we can use the condition that a vector, b vector, c vector are going to be equal to, scalar triple product of them is going to be equal to 0, which gives us that 1 minus 1 1, 3 1 2, 1 lambda and minus 3. The determinant of this is equal to 0 is given because already it is given that the vectors are coplanar. So this gives us that 1 into minus 3 minus 2 lambda plus 1 into minus 9 minus 2 plus 1 into 3 lambda minus 1 is equal to 0. From this we get minus 3 lambda, minus 3 minus 2 lambda minus 11 plus 3 lambda minus 1 is equal to 0, which gives lambda minus 15 is equal to 0, or lambda is equal to 15. So that is the answer for third problem. Question number 4. It is given that a vector is equal to I plus j plus k, b vector is equal to I, c vector is equal to c1 I plus c2 j plus c3 k. If c1 is equal to 1 and c2 is equal to 2, find c3, which makes a vector, b vector and c vector coplanar. So very simple substitution. So it is given that a vector, b vector, c vector are coplanar. That means the scalar triple product is equal to 0, which means the determinant of 1 1 1, 1 0 0 and c1 and c2 is given. So 1, 2 and c3, the determinant of this is going to be equal to 0. Applying the property of the determinant, we get 1 into 0 minus 1 into C3 plus 1 into 2 is equal to 0, which gives us minus C3 plus 2 is equal to 0, or we get C3 is equal to 2. That is the first part of the problem. The second part of the problem, it is given that C2 is equal to minus 1 and C3 is equal to 1. Show that no value of C1 can make A1, A vector, B vector, C vector coplanar. So we don't know what is C1, so let us try to find out the scalar triple product. So assuming these values, A vector, B vector, C vector, the scalar triple product will be given as 1, 1, 1, 1, 0, 0. Let us take C1 as C1, and C2 is given to be minus 1 and C3 is given to be 1. So minus 1, 1. Expanding this, we get 1 into 0 minus 1 into 1 plus 1 into minus 1. That becomes minus 1 because here there is no C2. There is no C1. So this becomes minus 2, which is not equal to 0. So whatever value C1 takes in this problem, the value of the determinant is never going to be equal to 0. Therefore, for no value of C1 will the scalar triple product be equal to 0. Therefore, they can never be coplanar. Let us do the fifth problem. Show that the 4 points with position vectors 4i plus 8j plus 12k, 2i plus 4j plus 6k, 3i plus 5j plus 4k and 5i plus 8j plus 5k are coplanar. So we have just seen in the property that is the seventh property. 4 points A, B, C, D are coplanar if AB vector, AC vector and AD vector are coplanar. Using this property, first we have to find AB vector, AC vector and AD vector. So just we have to subtract. So how do you subtract? AB vector can be found by subtracting B vector and A vector. So 2 minus 4. So minus 2i minus 4j minus 6k. AC vector is going to be obtained by subtracting A vector and C vector. C minus A. So 3 minus 4. That is going to be minus I minus 3j minus 8k. And AD vector is going to be equal to subtract D and A. So 5 minus 4, that is going to be I, plus 8 minus 8 is going to be 0. Then plus 5 minus 12 is going to be minus 7k vector. So now we need to find out what is the value of AB vector dot AC vector cross AD vector. That is equal to minus 2, minus 4, minus 6. From this we are taking these values minus 1, minus 3, minus 8 and 1, 0, minus 7. If we expand this, we get minus 2 into 21 plus 4 into 7 plus 8 minus 6 into 3. That becomes equal to minus 42 plus 60 minus 18, which becomes 0. Which means that since the scalar triple product is 0, AB vector, AC vector and AD vector are coplanar. Therefore, AB, CD are coplanar. Very simple problems these are. Sixth sum. Find x such that the 4 points A of 3, 2, 1, B of 4, x, 5, C of 4, 2, minus 2 and D of 6, 5, minus 1 are coplanar. So like the same previous problem, we have to find AB vector. AB vector is equal to I into, because 4 minus 3. 4 minus 3 is 1i. So 1i plus x minus 2 into j plus 4k. AC vector will be equal to I minus 3k, because 2 minus 2 will become 0. And then AD vector is going to be equal to D minus A, that is going to be 3i plus 3j minus 2k. So for condition of coplanarity, we know that AB vector dot AC vector cross AD vector is equal to 0. Applying this condition, we have determinant of 1 x minus 2, 4, 1, 0 minus 3, 3, 3 minus 2 is equal to 0. So applying the property 1 into 9 minus of x minus 2 into minus 2 plus 9 plus 4 into 3 will be equal to 0. So we have 9 minus x minus 2 into 7 plus 12 is equal to 0. So we have 9 minus 7x plus 14 plus 12 is equal to 0. We have 7x is equal to 35 or x is equal to 5. It's a very simple problem. Sum number 7. Show that the vectors a vector, b vector or c vector are coplanar if a plus b, b plus c and c plus a are coplanar. So it is given in the problem that a plus b, b plus c and c plus a are coplanar, which gives us that a plus b vector dot b plus c cross c plus a is equal to 0 because of the condition of coplanarity, which gives us that a vector plus b vector dot multiplying b vector cross c vector plus b vector cross a vector plus c vector cross c vector plus c vector cross a vector is equal to 0. We know that c vector cross c vector is equal to 0, so we can skip this and multiply these things with the remaining terms. So this gives us a vector into this term, a vector into this term and a vector into this term. And similarly we have to multiply with b vector, etc. So a vector dot b vector cross c vector plus a vector dot b vector cross a vector plus a vector dot c vector cross a vector plus, now multiply with b vector and so on. So plus b vector dot b vector cross c vector plus b vector dot b vector cross a vector plus b vector dot c vector cross a vector is equal to 0. We have already seen in property, that is, if two components are same in a scalar product a, b, then the value will be 0. So applying that property here, wherever there are two terms, that is, this is nothing but a vector, b vector, c vector plus a vector, b vector, a vector plus a vector, c vector, a vector plus b vector, b vector, c vector plus b vector, b vector, a vector plus b vector, c vector, a vector is equal to 0. So you know that this is 0 because there are two a vector. This term is 0, this term is 0 and this term is also 0. So therefore this implies we have a vector, b vector, c vector plus b vector, c vector, a vector. But since it is cyclic, this can be written as a vector, b vector, c vector plus again a vector, b vector, c vector, because this is also the property. Here we have seen in property that ABC is equal to BCA is equal to CAB. So using the property, ABC will also be equal to BCA. Therefore, we can write this as 2 times A vector, B vector, C vector is equal to 0, or A vector, B vector, C vector is equal to 0, which means that the A vector, B vector, C vector are coplanar. So if you are able to prove that the scalar triple product is 0, then the vectors are coplanar. So this completes the exercise problems for the supplementary portion of the chapter vectors. Let us do a few examples. Example 26, 27, 28, 29 are very similar to the exercise problems and they are very easy. So let me do example 30. Example 30 is similar to the exercise problem number 7. Prove that a vector plus b vector comma b vector plus c vector comma c vector plus a vector is equal to 2a vector b vector c vector. So to prove this, it's very simple. The LHS is going to be equal to a vector plus b vector dot b vector plus c vector cross c vector plus a vector, that is equal to a vector plus b vector dot b vector cross c vector plus b vector cross a vector plus C vector cross C vector plus C vector cross A vector. Since C vector cross C vector is 0, because cross product of the same vectors are 0, this is going to be A vector dot B vector cross C vector, because we are multiplying this with this, this with this, and this with this. So plus A vector cross B vector cross A vector plus A vector dot C vector cross A vector. Since these two are same, A vector is having 2 times, this becomes 0, this becomes 0, plus B vector dot B vector cross C vector plus B vector dot B vector cross A vector plus B vector dot C vector cross A vector. Again this becomes 0, this also becomes 0, because B vector is occurring 2 times here. So this becomes, only this term is remaining and this term is remaining. That is A vector dot B vector cross C vector plus B vector dot C vector cross A vector. So using the cyclic property, this is A vector B vector C vector, and this can also be written as A vector B vector C vector. So that becomes 2 times A vector B vector C vector. Hence proved. Let us do the 31st problem. Prove that A vector B vector comma C plus D is equal to ABC plus ABD. So LHS will be equal to A vector dot B vector cross C vector plus D vector. This is equal to A vector dot B vector cross C vector plus B vector cross D vector. That is equal to A vector dot B vector cross C vector plus A vector dot B vector cross D vector. That is equal to ABC plus ABD. So this is the RHS and hence proved. So with this we complete the supplementary portions of the chapter called vectors. Thank you.